and that's why I said it's too late, and that's why I didn't want to do it in here.
We should go on a field trip. Wait a minute,
Great. Hey, do you want to be the goalie for soccer? It's just goalie's not your position. I think you should be like. Yeah. I think you should be defensive.
I'm doing bowling defense. Just in case you don't get a goal.
You have to be really quick for goal.
That was you can do just in case we can gain.
Especially if someone does it up for 90. You'd have to jump all the way to one side and hit it.
Make sure you're writing down your homework, getting your stuff situated, and then getting ready to work on your Socratic. Okay?
Go for points. That's probably what you should do.
In general. So? Yeah. How was it for me specifically? You knew how to volunteer today? Juliana, what about you?
I'm already going to voluntary for one other subject, so I'll do science with it in there.
That's fine. And Sophia, are you taking your test today?
Yeah.
Okay. You take it in study hall?
Huh?
You take it in study hall?
Yes.
Sophia, did you get 11.3 done?
I thought I had it done.
You might have yesterday. You did yesterday afternoon. Did it yesterday afternoon.
No, I didn't, but I'll get it done.
That's fine. Are you going to study hall either way?
Yeah.
Or voluntary either way?
Yeah.
Do you have a pass? Madison, you still booting up?
No, it's not.
If you finish your credit, go ahead and get your notes open. We're going to do 2 sections today. Neither one very long, neither one very crazy. After we go over some credit, we'll talk about what's going on the rest of this week. And then we'll go into the 2 sections for today. Go quick. Open up your notes square. Notes and textbook. Did you get all those notes I sent you yesterday? Julian, did you get them? Do you have the notes or do I need to send them to you?
No, I have to send it to you. I'll check it out.
I'll share them with you in the class. And you can copy them. Okay. And Sophia, what about you? Did you get all the notes?
Yeah, I send it to you.
You need them? Do you need them?
I don't have them like checked, but I did them.
Okay. Do you want me to send you the copy so you can check them? I'll send it to you guys in the class. All right. Let's go through this. Then we will talk about what we're going to do. So, magnetism is the force of attraction. True or false, Jared?
False.
False. It is the force of attraction and what else? Yeah?
Repulsion.
Repulsion. Very good. Attraction and repulsion. Okay. Which of the following would be attracted to a magnet, Olivia?
I don't know.
An iron nail. Good. What's happening to these magnets, Sophia? See, they're attracted to one another because they have opposite poles. Opposite poles. What would happen if they had like poles?
They would repel.
They would repel. Good. Bar magnets always have what, Madison McWhorter? A. 2 poles, 1 north and 1 south. Good. Where are the magnetic lines of force closest together? Squire?
On the poles.
On the poles. Very good. Remember, we saw that yesterday in lab when you dropped those iron filings. Strongest are on the poles of the magnet. Which of the following is an example of a natural magnet? Madison Denny? C. Lodestone. Very good. Iron and nickel can become magnets, but they are not naturally occurring magnets. Lodestone is the only one on the list that's a naturally occurring magnet. Thank you for not putting cork today. Temporary magnets are what, Juliana?
Easy to make. B.
B. Easy to make and do not keep their magnetism very long. Make sure you read the whole option because the first one says easy to make and keep their magnetism. They don't keep their magnetism very long. And we'll talk about that a little bit more today. Permanent magnets are what? Lily? See, hard to make, but they keep their magnetism for a long time. Permanent, hard to make. Okay, it's permanent habits that are hardest to keep, right? Or hardest to get. Isaac Newton said the Earth was similar to a bar magnet. Callum.
False.
False. Who said it?
And William Gilbert.
William Gilbert. Very good. William Gilbert. Okay, Newton was the guy that did the 3 laws we talked about earlier this year. The combination of particles from the sun reacting with the Earth create the northern and southern lights, which are also known as what, Juliana? Auroras. Auroras. Very good. All light is luminous, so luminous light doesn't really make that much of a difference. Okay, who discovered electromagnetic induction, the ability to create magnets? Sophia? C. Oersted. Very good. Faraday and Henry, they told us that you could use magnets to create electric current, and Edison did the light bulb. Okay, an electromagnet is a temporary magnet. Tyler?
False. True. No, false.
True or false?
False.
False. That's actually true. Why is it true? Why isn't it? We're going to talk about electromagnets more today, but why is it true? If I take the electricity out of an electromagnet, what happens?
It's just a magnet.
No, it's not even a magnet. It's just a piece of metal. There's no electricity running through it anymore. We'll talk about this more today. Okay? Which 2 scientists discovered that electric current could be created by using magnets? Jared? Henry and Faraday. Good. No suck-ups today picking Buckley and McGuire. Okay? Edison and Tesla, remember, they're alternating current and direct current. Elon Musk and Steve Jobs are modern-day inventors. And Miss McGuire and Mr. Buckley are just the best teachers ever, right?
No.
I don't know if I really appreciate any of that. All right. So let's see. For homework tonight, you need to do 11.6 and 11.7 checks and worksheets. Make sure you read and take notes over 11.8. I'm not going to be here, again, just to remind you guys, I'm not going to be here on Thursday or Friday. So tomorrow we'll do 11.8 as a class. On Thursday, you'll do 11.9. Okay? Friday, you'll come in, we have a video to watch, and you'll start on your challenges, your end of chapter challenges, which I will send you guys. Yeah.
Is our test on a Tuesday?
Your test is on Wednesday.
Okay.
So a week from tomorrow, we'll come in. Monday, we'll finish whatever challenges you didn't finish on Friday. Tuesday, we'll play our review game. Wednesday, we'll take our test. Okay? Any questions on anything coming up?
Nope.
All right. Let's jump into the book. We're going to start reading today, talking about electromagnets. When we get through this section, we're then going to watch a video about how they make magnets, talk specifically about electromagnets, so it'll be kind of cool. It's not very long. It's only about 7 minutes, and then we'll do this section on transformers. And I mean like the electronic transformers, not the one I have in my office. Okay. Which one I have in my office? It's a transformer. Anyway. All right, so first off, we're creating our notes. How many boxes do I need for our notes?
4.
3 or 4? How many say 3? How many say 4?
Wait, yeah.
Okay, remember we're going by subheading, so I've got 1, 2, and 3.
But you need 1 for your checks.
But I need 1 for my checks and worksheets, so the answer is 4. Good, Tyler. Okay, 11.6, all labeled, ready to go. Let's start reading. Jared, why don't you start us off?
A wire carrying an electric current always has a magnetic field around it. The magnetic field around a straight wire is not very strong. If the wire is wound into a coil, the magnetic field becomes much stronger. The magnetic fields around the coils of the wire add together. The more coils you add to the wire, the stronger the magnetic field will be.
Good. All right, what'd you guys have? What's important in that section that we need to write in our notes? Jared?
The wire is around the coil, the magnetic field becomes stronger.
Okay, so when you wrap a wire,
Around the coil.
what happens?
The magnetic field becomes stronger.
Oh, the terrible spelling errors. Good. around a coil, field becomes stronger. Good. Wire?
A wire carrying an electric current always has a magnetic field around it.
The wire carrying the electric current doesn't have the magnetic field. It amplifies the magnetic field.
Okay.
So we could say that. We could say the current through the wire amplifies the magnetic field. And we have terrible spelling errors. Okay? Bless you. Anybody got anything else? Mm-mm. All right. Let's go back to electromagnets then. Let's start reading about electromagnets. Squire.
Wrapping coils of wire around a piece of iron will produce a strong magnet. This type of magnet is called an electromagnet. The iron in the center of an electromagnet is called a core. An electromagnet is a temporary magnet. As long as the current is flowing through the wire, the electromagnet has a magnetic field. When the current is turned off, there is no longer a magnetic field. The strength of electromagnet can be increased in two ways. Adding more coils of wire around the iron core makes an electromagnet stronger. Increasing the current through the wire also makes the electromagnet stronger.
Okay, good. What do we got that's important? Julia?
Temporary magnet made by wrapping a current carrying wire around an iron core.
Good. Temporary magnet made by what?
Wrapping a current carrying wire around an iron core.
Losing that really butchered word temporary. I almost got it all now. Okay. What else? Somebody besides Connor. Cal?
Temporary magnet?
Well, we got that it's a temporary magnet. Part of the definition. Temporary magnet. Jared? No? Squire?
Wrapping coils of wire around a piece of iron will produce a strong magnet. Or do you already have that?
Well, that's pretty much the definition of it. Okay, that's how we create an electromagnet. We take a piece of an iron core and we wrap wiring around it, then we run current through it and we create that electromagnet. Is there anything else? We can move on.
I don't think I have anything else that's important.
Alright, let's move on. So let's talk about the use of electromagnets. Read that last section on use of electromagnets. Madison, Denny.
Electromagnets have several important uses. They are used in many devices, including radios, telephones, and computers. Large electromagnets are used to lift heavy pieces of metal. Electromagnets are very useful because they can be turned on and off.
Good. Alright, what do we got? Juliana?
Use in radios, telephones, and computers.
Good. Sophia?
Large electromagnets are used to lift heavy pieces of metal.
Okay, so we can say, can lift heavy pieces of metal. I also said televisions. Good. Anything else?
They can be turned on and off.
Good. Can be turned on and off.
So all electromagnets can be turned on and off.
Mm-hmm. Correct. because you can take the current, you can remove the current, and then put it back in. That's what makes them so useful. All right, everybody got that? All right, let's compare our notes, see how we did. All right, first one is increasing the number of coils causes the magnetic field to become stronger. Pretty much exactly what we have, right? Good. Let's take the second one. Electromagnets, temporary magnets made by wrapping current carrying wire around an iron core. Good. And then they talked here about how the strength of electromagnet can be increased. We missed that, so let's add that to our notes. Remember, when you add it to your notes, you want to add it in a different color so you know that this came from the teacher or it came from some source other than you. I'm going to do mine in red.
Wait, what did we miss?
You're going to add, I'm going to type it right here, but it's fine. Strength can be increased in two ways. Number of coils and increasing current. You know, we'll just keep it simple. We'll underline it. Okay. You guys can add that to your notes. I'll add it to mine.
Wait, does an electromagnet have to be magnetic?
The core has to be. The core has to be magnetic. Everybody got that addition? Okay. And the last one. Lifts heavy pieces of metal, radios, television, computers, and can be turned on and off. I would say we got that last one pretty well perfect, don't you?
Yes.
All right, so electromagnets are that temporary magnet. Why do we use iron cores? And? No, not really. We have plenty of things we could make that would be stronger than iron. Why?
Because iron is tougher.
Does that have anything to do with its toughness? Think about items that we can make to be magnets or things that will attract magnets. What were those three
Oh,
that are easily magnetized?
iron,
Iron,
cobalt,
cobalt,
and nickel.
nickel. So those three elements are easily magnetized. So when we create magnets using those three elements, they're just easier to line up. We don't have to work at them as hard. It doesn't take as much current. Okay, you could make an electromagnet with a battery and a little iron nail, and that's all you would need. Yes, Connor?
So the picture of that thing, like in the scrap yard, or whatever, was that made out of steel because it's stronger?
No, it would probably have an iron core in it as well. And what's happening is the coils are wrapped around inside of the iron core. That's just what lets it turn on and off. All right, we got a short video on, it's only about 7 minutes long, on magnets and electromagnets. It shows you kind of the biggest electromagnet in the world, which is kind of cool. We're going to watch this real quick.
Magnets. You just can't get away from them, especially if you're made of iron. They are everywhere, from your headphones to your PC to cash at the cash point. In fact, magnets are the little scientific secret behind almost every clever device you can't do without. But when it comes to making the attractive little fellas, how do they do it? You're looking at the biggest magnet on the planet. It is the planet. 1,800 miles below the surface, the Earth's outer core is a vast 1,300-mile wide churning ball of liquid iron and nickel.
Remember,
The
those two
circular
elements are
movement of this
really
massive
magnetic.
molten iron creates the Earth's magnetic field, which makes compasses point north. But the Earth's magnetic field is still quite weak. A simple magnet like this produces a magnetic field 200 times stronger than the Earth. These bar magnets are made from a special iron alloy that's been exposed to a powerful magnetic field. The atoms inside have realigned themselves, creating permanent north and south poles. But if you want a really powerful magnet, then you need an electromagnet like this. 200 times more powerful than a simple bar magnet, it can temporarily magnetize other metals until you turn the power off. In fact, if you've got a strong enough magnetic field, you can affect almost anything. It doesn't even have to be metal. Here, a powerful magnet is actually levitating a strawberry. Of course, to make floating strawberries, you need a really, really powerful magnet. They don't come more powerful than the magnets here at the Mag Lab just outside Tallahassee, Florida. In this building are the most powerful magnets in the world. Scientists here are using their super mighty magnets to do all kinds of stuff, from developing new forms of transport to revolutionary new medical treatments. For groundbreaking research like this, you need magnets that offer precision and power, and an off switch wouldn't hurt either. MagLab boss Mark Bird is strangely drawn to magnets.
I can talk about magnets all day.
Mark explains how his magnets work using an ordinary household nail.
You take a nail and you take some wire, you wind it up, you stick a battery in here, and now what happens is current flows through this wire, it goes around and around in circles, it makes a magnetic field in the center, and now we can pick up paper clips with it.
The key to Mark's electromagnet is not the nail in the middle. It's the spiral of electric current running round it that whips the atoms of whatever's in the middle into line. But here they don't like messing around with little magnets. They like working with big, super powerful and slightly scary magnets. In the heart of the building is the biggest magnet ever built, the 45 Tesla hybrid magnet. It's so powerful that just being in the same building as this thing wiped clean half our camera tapes, which was extremely annoying. So magnetism is when atoms or subatomic particles like to line up in a particular way when squirted with an electric charge. Sort of. Clear? Well, never mind. Here's a magnet so utterly humongous it could rip out your fillings from half a mile away. The 45 Tesla is 4,000 times more powerful than one Mark demonstrated earlier. But if it was 4,000 times bigger, it would be a quarter of a mile
Jared,
long.
head up.
The key to making a really powerful magnet is making it compact. And the way they do that is by using loads of magnets to magnify each other's magnetic fields.
This is the core of the 45 Tesla hybrid magnet, the most powerful DC magnet in the world. There's 5 coils. You see 4 here because there's actually 2 nested here that you can't really see. So this is an insulator that goes around the first coil, and then these go inside the second coil, another insulator, the third coil, another insulator, the fourth coil there.
If you just ran electric current through one of these coils, it would make a powerful magnet on its own. But when they're stacked inside each other like Russian dolls, each coil is boosted by the bigger coil outside, creating a massively amplified magnetic field. It's a clever idea, but making it work requires superhuman patience. Fortunately for MagLab, Jim here is possibly the most patient man in Florida. Putting together the thousands of metal plates for the coils that generate the magnetic field takes Jim 6 months. If he just stacked the 0.2mm thick copper sheet in layers, the current would travel straight up, and no spiral means no magnetic field. So Jim places fiberglass insulation on either side of the copper sheets, slowly building an incredibly dense spiral.
So what the insulator is doing, it's stepping around the coil, and it's acting like a spiral staircase. You tip that off, and there you go. You have another turn on a resistive magnet. Hey, let's go build another one.
The 45 Tesla hybrid turned out to be too much magnet even to look at safely, but we did manage to film its little brother, the resistive magnet. Inside its steel casing, copper plate coils, exactly like the ones we saw Jim make, exert a magnetic field 400,000 times more powerful than the Earth's. It's a valuable tool for research, and when the boss isn't looking, it's good for party tricks too. So, just for how do they do it, they showed us a neat little bit of magnetic magic. Our glamorous assistant, Tim Murphy here, drops a chunky 2-kilogram aluminium tube into the top of the machine at 6 p.m. The intense magnetic field induces a current inside the tube, creating an opposing magnetic field. The two fight it out, slowing the tube's fall. When it finally hits the floor 12 feet below, it's 6:02. 2.5 minutes have passed. Not magic, of course, just magnets. What?
Alright. That was it. Alright. So, just kind of showing you how they make some really big electromagnets. But they all follow the same principle. Wrapping coils to create or induce a magnetic field.
But they're not actually using a magnet.
No. They're forcing those particles to line up. Like we force you to line up to go out to recess. Okay? The electric current flowing through forces the particles inside of that core to line up, giving it that north and south
How
pole.
do they get the core that much atoms in to make it that powerful?
It's not the atoms they're giving, it's the electric current. So it's the amount of electricity that they're running through to make the coils line up.
So the more electricity running through it, the more powerful it gets.
Mm-hmm. So remember, we just talked about our notes. There's two things that make an electromagnet more powerful. One is the amount of coils, the amount of time it wraps around, and the other is the amount of current that they push into it. Yeah.
You think this would be like the future of like if space travel, like gravity? You know what I'm
Gravity
talking
and magnetism are two different things.
I know, but
So no would be the answer to the question. All right, let's start reading into section 7, talking about transformers. Again, how many boxes should I have set up on my notes? 4. Okay, 1, 2, 3, and then the fourth one is for checks and worksheets. So let's start reading about transformers. Olivia, why don't you start us off reading about transformers?
Suppose you wrap 2 coils of wire around a nail. You attach one of the coils to a dry cell and a switch. The coil is called a primary coil. You connect the other coil to an ammeter.
Ammeter.
This is a secondary coil. When you close the switch in a primary coil, the ammeter shows that a current flows in the secondary coil. This current quickly dies out. When you open a switch, current again flows in the secondary coil. Again, it quickly dies out. To keep current flowing in the secondary coil, you must keep opening and closing the switch.
Good. And Jared?
In transformers, the device that uses alternating current in the primary coil to induce a current in the secondary coil. The primary coil is connected to a source of alternating current. In alternating current, the flow of electrons changes direction regularly. Alternating current in the primary coil induces a current in the secondary coil.
Okay. All right. So what did you guys have that was important? What's important in that section? Somebody besides Connor. Connor, as much as I love you, other people got to talk to. Sophia?
A transformer is a device that uses alternating current in the primary coil to introduce a current in the secondary coil.
Device that uses alternating current to
Induce
induce
a current in the secondary.
A secondary coil. Good. What else? Is there anything else for that one? Huh? So what a transformer is it's basically a way to continue moving electric current, to move electric current from one circuit to another with using only one source. Make sense? Sometimes you'll have a source where you need to send it, like when you're sending power from a power plant through power lines. You can't just have one line running directly to your house, right? You got to run it to multiple houses. So transformers are what we use to help keep that current moving. All right, let's read about step-up transformers. Juliana, read about step-up transformers.
Transformer can be used to increase voltage. The kind of transformer is called a step-up transformer. Step-up transformer has more turns of wire in the secondary coil than the primary coil. The more turns of wire there are in the secondary coil, the higher the voltage will be. Power campaigns use step-up transformers to send high voltage electricity over long distance.
Good. All right. What's important in step-up transformers? And we'll talk about what they are. Cal?
Used to increase voltage.
Good. Juliana?
Turns more wire in secondary coil.
Okay. More turns in secondary coil. Good. Sophia?
It's used in power companies.
In power companies, so using, we'll say in power lines. How about that? Good. Anything else? Wire?
Power companies use step-up transformers to send high voltage electricity over long distances.
So we'll just add to this note. Used in power lines to send voltage long distance.
And a transformer can be used to increase voltage.
Well, that's what we have. Used to increase voltage. Okay, so let's look at this picture that I got up right here. So this is a step-up transformer. Okay? Now, you always look at transformers from left to right, like you're reading a book. Okay? Notice in the primary coil, there's only 5 little twists. We can count them. 1, 2, 3, 4, 5. Right? But on the secondary coil, there's 20 turns. Okay? There's more in the secondary than the primary, and the voltage has equally increased. 4 times as many turns, 4 times as much voltage. Okay? Think about it this way, that I'm a pretty short guy, right? If I want to get taller, I have to step up, right? So I'm taller now, right? Just like with the voltage, there's more voltage in a step-up transformer, just like there's more height for me when I stand on a chair. I think that people are actually this tall naturally. Weird. All right, let's read about step-down transformers. If step-up transformers increase voltage, what do you think step-down transformers do?
A transformer can also decrease voltage.
Thank you for reading the first sentence, but let's have Madison McWhorter read the rest
Oh,
of it.
yeah, I forgot we had to read it.
That's okay. Madison?
Gotcha. No.
Can you see it from up here?
Yeah. A transformer can also decrease voltage. A transformer that decreases voltage is called a step-down transformer. A step-down transformer has fewer turns of wire in the secondary coil than the primary coil. The fewer the turns of wire in the secondary coil, the lower the voltage will be. Step-down transformers lower the higher voltage carried by power lines.
Good. All right, what do we got for notes? Juliana?
Decrease voltage.
Decreases voltage. Okay? besides Julian and Squire? Jared, what do you have?
It also can increase step down transformers will lower the high voltage very long lines.
Okay. Why would we want to do that?
So we could do control
Well, if it's lowering it down,
in case.
why
there
would
was
we
a
want to?
problem.
Why would we want to lower the voltage in power lines? Where might they be going where we don't want, say,
I know.
1,000 volts? I know you know. I'm trying to give somebody else maybe a chance to answer.
To houses.
To houses, to homes. Okay? I know you had it, Squire. Okay? To homes. So that we don't have 4,000 volts of electricity coming into our houses. Okay? Most of your houses run on about 240 volts.
I was gonna
And
say
then you can
something a
split it
little
out to
bit differently.
120.
I was gonna say like they would want to send more to like a city than like a town.
Right. But why would we need to step down? I wasn't answering the question I was asked. Why would you step down?
Well, that's understandable now because you don't want to have something that you're not using, like surplus power. Like,
Right. You don't want too much. Okay? What else do you have? Anything else? Madison Denny? What do you have?
Has fewer turns.
Which one? Very good. It has fewer turns in which wire?
The secondary coil. Or the end of the
Good. Fewer turns in the secondary coil. Good. Alright. Again, if we look at our picture, step down transformer, notice, has 50 turns in one, only 10 turns in the next. That would be like me up here, very tall, stepping down, and I'm shorter, right? Step down transformers, shorter in height. Step down transformers on screen or in actual real life, less voltage. You got it? Sure? All right, let's compare our notes and then we'll be done for today. Split the page, didn't I? All right, first one, transformer, device in which alternating current in one coil of the wire induces a coil in the second. Good. Second one, step up transformer, increases voltage, more turns in the secondary coil. We have the extra one of used in power lines, which is fine. And the last one, step down transformer, fewer turns of wire in the secondary coil than the primary coil. Good. Any questions? Everybody got what they're doing for homework? Everybody ready for lunch?
Yeah.
Back to bed.
Alright, how about your trapper son come around and sign you off? You got about 2 or 3 minutes until the bell rings.
How's that fun fact true?
Yes.
English and French?
That's just how they teach it.
And there's probably more people in China than the US.
They are the most populous country on the planet. Trapper out, please.
In Japan was.
I don't know why. I thought they were school thing.
You tired again, Tyler?
So what time do you go to bed?
I went to bed at 11.
Tyler,
I went to bed at 1:30 last night.
what time do you
I went to
go to
bed
bed?
too.
11